Iron-Impregnated Bamboo Biochar. Antibiotics. Antibiotics are antimicrobial substances that are active against bacteria and are widely known due to their therapeutic uses. These substances are used to treat fatal infectious diseases and open possibilities for treatment of cardiovascular diseases, anti-cancer, anti-tumor agents. Aside from human health, antibiotics can also be used in the promotion growth of animals, biocides in toiletries and hand cares, in pest control and in household cleaning agents. Due to this wide application, massive production of antibiotics, which is million metrics of tons of antibiotics have been produced. An estimated consumption rate in 76 countries, including the Philippines, was made by Klein and his colleagues. The results showed that there is a 65% increase in the consumption rate from 2000 to 2015, wherein 21.1 billion defined daily doses increased to 34.8 billion defined daily doses in just 15 years. We can see how massive the production and usage of antibiotics these days. So you may ask, how can these antibiotics find their ways to the environment? Most of these antibiotic contaminants came from hospitals. Whenever we take antibiotics, typically 30 to 90% of the active compounds of that antibiotic are being excreted and flushed down to our toilets, which means that our sewage plants have to treat massive amounts of antibiotics, which are incompletely degraded and removed. Humans are not the only source of antibiotic contaminants. Animals can be a source too. They excrete manure into the land and wash off into the rivers, lakes, or groundwaters. And of course, high amount of antibiotic contaminants came from the manufacturing plant itself during the production and the formulation. So you may ask, how antibiotic contamination be a global problem? Well, the antibiotic contamination creates a reservoir of antibiotics in the environment. And this promotes antibiotic-resistant development in human and animal pathogens. And how risky having an rising antibiotic-resistant bacteria in our environment. This could endanger the efficacy of the antibiotics, surpassing the existing antibiotics, and therefore, the treatment will no longer be possible. Actually, according to the UN and WHO, it could actually kill 10 million people by 2050. So among the most used antibiotics are tetracycline. Tetracycline belongs to the polypeptide family based on the naphthacene tetracycline ring system. Its wide application is on human healthcare, veterinary medicine, and agriculture. It is also considered as one of the pseudo-persistent pollutants, which are frequently found in sewage, activated sludge, digested sludge, and effluents in municipal wastewater treatment plants. Various treatments and processes are used in the wastewater treatment facilities. However, conventional treatment methods such as filtration, sedimentation, coagulation, flocculation, and other biological treatment processes, as well as adsorption and membrane processes, do not have the ability to degrade these pharmaceutical products. Hence, advanced oxidation process is used for this purpose. One example of an advanced oxidation process is the Fenton process. Fenton process uses metallic catalyst, which is usually iron catalyst, reacted to hydrogen peroxide in order to produce hydroxyl radicals, which are the one responsible for the degradation of the tetracycline. There are two types of Fenton process, the homogeneous and the heterogeneous Fenton process. Among the two, heterogeneous Fenton process is most preferred because it does not generate iron sludge and where catalyst can be recovered. However, it requires a loading material. And among the loading material, biochar is an excellent one. Why? Because of its high porosity, readily availability, relatively low cost, and eco-friendliness. And there are various kinds of renewable sources being used as feedstock for biochar. And among these, bamboo biochar is an advantage due to its higher porous structure and larger specific surface area compared to other feedstock. Up to date, no study has been conducted yet on the impregnation of iron catalyst in the degradation of tetracycline. So this study aimed to evaluate the viability of Fe biochar as catalyst in TC removal via Fenton process, specifically to synthesize and characterize an iron biochar for tetracycline removal from aqueous solution to assess the effect of different parameters such as the Fe biochar dosage, hydrogen peroxide concentration, and solution pH on the tetracycline removal. And finally, to determine the optimum conditions for the said parameters. This study will help in reducing and possibly eliminating the tetracycline concentration in wastewater while minimizing the iron sludge generation, promotes catalyst recovery, and giving value to the abundant bamboo wastes. For our methodology, we have two phases: the preparation of the iron-impregnated bamboo biochar and the Fenton process itself. So for the preparation of the bamboo biochar, the bamboo waste, specifically the stem part, was spiralized, treated with 1 molar nitric acid to remove the metallic impurities, grounded and sieved using 250 microns mesh screen. The preparation of the iron solution is simply dissolving ferric nitrate nanohydrate on distilled water, which produces 50 ppm of the solution. So for the impregnation of the iron bamboo char, it was stirred in the iron solution with the bamboo biochar for 8 hours using a magnetic stirrer. The resulting bamboo biochar, impregnated and non-impregnated, were characterized using FTIR or Fourier transformed infrared rays and EDX or energy dispersive X-rays. So for the phase 2, which is the Fenton process itself, which includes the tetracycline removal. So for the preparation of tetracycline solution, tetracycline hydrochloride or tricor was dissolved in distilled water, producing a 50 ppm TC solution. For the tetracycline removal, box Benken design was used, a response surface methodology, in order to determine the number of trial runs and to determine the optimum conditions. So these are mixed. The factors being varied was Fe biochar dosage, varied from 2550 to 75 milligrams. Hydrogen peroxide concentration varied from 0.075 to 0.75 molars, and solution pH from as 4, 5, and 6. So these are mixed and then agitated for 1 hour. A 5 ml sample solution was tested using UV spectrophotometer. For the result and discussion, for the characterization of bamboo biochar, using FTIR, a new broad peak was observed, implying an alteration in the surface functional groups of the biochar before and after the impregnation. And while for the EDX, or the energy dispersive X-rays, we can see that there is the presence of iron in the impregnated bamboo biochar, which suggests a successful iron impregnation in the preparation of the catalyst. So for the effect of different parameters on the tetracycline removal, the effect of solution pH on TC removal can be seen at the figures. At acidic conditions, TC removal is increased. Since the pH was within the acidic range, satisfactory TC removal was obtained for all levels. for the FE biochar dosage on TC removal, it can be seen that there is a parabolic relationship. As FE biochar dosage is increased, generation of OH radicals also increase, thus higher TC removal is obtained. However, after reaching the maximum consumption of the catalyst, which can be observed at 50 milligrams, ferric ions could scavenge hydroxyl radicals in competition with the tetracycline. And for the effect of the hydrogen concentration on the TC removal, we can see an increasing trend. Hydroxyl radicals account for the degradation of tetracycline, thus, tetracycline removal increased with the increasing hydrogen peroxide concentration. So for the mathematical model equation generated using the design expert, it can be seen in the screen. This was fitted in a reduced cubic model with factors the A as FE biochar dosage, B as H2O2 concentration, and C as the solution pH, respectively. So for the optimum conditions, FE biochar dosage was set at minimum. The H2O2 concentration was set at minimum also. Solution pH as within range, and the maximum TC removal as maximum. So as generated in the design expert, it was found out that the optimum conditions was found to be at 41.33 milligrams FE biochar, 0.05 molars hydrogen peroxide, and at pH 4 with maximum TC removal of 38%. So in conclusion, FE biochar was successfully synthesized and was found to be an effective catalyst in the removal of TC via heterogeneous Fenton process. FE biochar dosage, H2O2 concentration, and solution pH have significant effect on TC removal. At optimum conditions of 41.33 milligram FE biochar, 0.05 molar H2O2, and pH 4, a maximum TC removal of 38% can be obtained. For our recommendations, we highly recommend to widen the range of the process parameters in which TC removal is investigated. Study the kinetics of TC removal using FE biochar catalyst, and to extend its application on the treatment of the actual wastewater. So I hope you get something from our study. Thank you for listening.
Thank you, Ms. Calangi. For our last but not the least presenter, he obtained his BS Electronics Engineering